So here I am on a late Friday afternoon with Wim van Westrenen at the Vrije Universiteit of Amsterdam, or in Amsterdam. I'm sure I'm murdering that
No,
pronunciation of
that's
it.
actually pretty good. That's pretty good.
Who is a planetary scientist and a lunar scientist. And we've been discussing lunar science on the moon. And we're just outside your lab. Tell us about the Earth VU, kind of a play on words or play on, it's Earth VU,
Earth Fusion Labs,
Earth
yes.
Fusion. And I guess the VU is for
For Vrije Universiteit, yes, the name of the university.
So
Yeah.
tell us in the interview you were telling me that this lab incredibly allows you to simulate conditions at very high temperatures and very high pressures. And tell us how that happens.
Yeah, that's right. So we use big presses to compress tiny pieces of rock to high pressure, and while they're being crushed, we can also heat them to 1500 degrees or more to indeed simulate what happens in the interior of the moon, mostly in our lab, but also the Earth or Mars. Any rocky body you'd like to study, we can recreate what goes on inside them. And we can study the properties of those rocks, how the minerals change because of heating or because of crushing the material. And we can study their composition and their physical properties like their density, and then compare that with observations from space missions.
And the temperatures and the density and the pressures are pretty incredible. Can you give us an example?
Yeah, so here the very highest pressure we can reach here is 250,000 atmospheres of pressure, so 250,000 times higher than the air pressure outside on
Good
Earth.
gosh. And we're at 1 bar.
Right.
And so you're saying it's 250,000 bar inside this.
Yes, inside the middle of the press, and that's equivalent in the Earth. It would be about 700 kilometers underneath our feet, so about a tenth to the middle of the Earth.
And Venus is 92 bar, and
That's at the surface, yeah.
enough to crush, most missions. That's been a huge technological problem for missions to Venus for decades, and we're talking 250,000 times Earth's atmosphere.
Yeah, that's right. Which is what happens inside the Earth, and of course the Moon is a lot smaller than the Earth, so the maximum pressure in the Moon is about 50,000 atmospheres, and we can sort of travel to the middle of the Moon in a lab like this.
And what about the temperature?
The temperature, yeah, it can be a couple of thousand degrees, so like 5 or 6 times your pizza oven, so to say.
Which are pretty hot, which is pretty hot. So interestingly enough, after 50 years of study of the moon rocks from Apollo and this most recent successful Artemis 2 mission, you were telling me that we still don't have a great understanding of the moon's formation. We have some ideas, some good theories, but tell us why you say that.
Yeah, so we have a reasonable idea, the idea of this giant impact between the Earth and another planet that people call Theia. There's a sort of mystery planet that crashed into the Earth, and the moon is supposed to have formed from the debris of this collision. Part of that debris went into orbit around the Earth, and that became our moon. So the general theory is a good one, a very nice one. It explains many things, but one of the things it has difficulty explaining is actually the composition of the moon rocks as we have them from Apollo and some of the Chinese sample return missions, and that is actually still a mystery. So we're still not 100% sure that this giant impact theory is correct. And that's very exciting, at least to me, that even so many decades after the Apollo missions, there's still really fundamental questions about the moon that we haven't quite solved yet.
But we've ruled out a couple of theories. One is a capture.
Yes, so the idea that the moon formed somewhere else in the solar system and was then caught by the gravity field of the Earth, we know that's not true because of the Apollo samples. So these samples are too similar to the Earth to be able for the moon to have come from somewhere else. If the moon came from somewhere else, the rocks should look, for example, a bit like Mars rocks, and we know they don't. They look far more like the Earth than they should if the moon was captured. So we know that's wrong. We also know that the co-formation theory, which was another major theory before Apollo, was wrong. The idea that the moon and the Earth formed at the same time, at the same place, where we are now, then the Earth and the moon should have looked a lot more similar than they are. And we know that's not true because the moon only has a small iron core, for example, and the Earth has a huge one. So that doesn't fit with that theory either. And that's why, in the end, the giant impact model was developed. On the basis of the evidence from the Apollo rocks, we knew that the other theories were all wrong, and then the new theory was developed after the Apollo program ended.
And the hydrodynamic models today are robust, but the geochemical compositions that we find in the moon rocks and what we find on Earth are too similar, is that right? Or
in a way, they're too similar. So the latest iterations of the giant impact models are getting closer and closer to getting a match between the moon rocks that we see and the moon rocks that should form as a result of this giant impact model. But they're not identical yet. So there's still a small difference between what we predict the moon composition should be and what it really seems to be on the basis of at least the rocks we have so far.
And initially in my book, I remember in my book Distant Wanderers, which came out in 2001, I remember describing the moon impacting object as Theia, which was termed Theia, as a Mars-sized object. But that, in the 25 years since, that's there's still not agreement. You're saying what? It could be an object as small as Mercury or an object as large as our present Earth that impacted Earth.
Yeah, so the latest iterations of these hydrodynamic models suggest that the Mars size is probably not the best sized impactor to make the Earth-Moon system, and that it works better, it matches better with the composition of the moon rocks if we either have a smaller impactor, so smaller than Mars, but one that arrives much faster than a Mars-sized impactor would, or we have a huge impactor, actually as big as half the Earth itself. So that would be much bigger than Mars. So that shows one of the problems we still have on this moon formation model, that we haven't yet really agreed on how big the impactor would be and how fast it arrived and those sort of basic variables.
And we still don't know exactly the timing of the impact, right?
No, that's another issue. So we try and measure the age of the moon by measuring the age of moon rocks. But the problem is that those moon rocks all consist of solid minerals. But we know that those minerals all formed from molten rock. So we know there was magma on the moon first. Because of the giant impact, the moon materials got super hot, thousands of degrees. So they predict to have completely melted. And then those minerals that we find now in the moon rocks formed when you cool down the magma. And we can't measure how long that cooling really took. So we can only measure the result, the mineral that was formed at the end. But then you can still have a debate, did it take very long to form that from a magma? Or was that very rapid? So that's also still a problem.
So what should we be doing? What should the scientific community, the research community, the lunar science community be doing to solve these mysteries that we've just outlined?
Well, one of the main things they could do is try and get more samples from more different locations on the moon. So we have these Apollo samples, and we have some subsequent samples from return missions, from robotic ones from China, but still they only cover a limited area of the whole lunar surface. So one question that you can still always ask is, how representative are the rocks that we actually have on Earth? Maybe there are other areas on the moon where the rocks are really totally different, and that could affect everything we think about the moon, actually, including its formation. So getting more samples, it sounds easy, or maybe, but it's really true. If we get samples from different locations on the lunar surface, we could really advance lunar science.
And you think that a lot of this could be done robotically, particularly with the AI that's being developed now? Mm-hmm. I mean, the autonomous navigation systems that we're using here on Earth for taxis, for instance, or even for drones. If you could combine a drone, a drone with some sort of surface rover, some sort of physical, some sort of craft that could both rove and fly at will, and sample, and maybe return it to a central location where you could get these samples back.
Yep.
We wouldn't really need to send humans to the moon, would we?
To get samples, you're right. To get more samples, you don't necessarily need to do that with humans. I mean, if you have a scientist, like a planetary scientist or geologist going there, I think that would help. You can make maybe quicker decisions or make different decisions than AI on what you would sample. But basically, if we're asking a scientist for more rocks from different areas, that could easily also be done robotically. That's true.
And I guess ideally you would have both. You would have a human mission with boots on the ground working with robotic technology.
Yes, of course. That's like the dream come true for lunar science. Sure.
So what haunts you most or puzzles you most about the moon? I mean, when I look at the moon, it's a beautiful object, but it's haunting because it is so lifeless, and it's so totally different than our own planet, and yet it's so near us. It's similar to Venus, which is, Earth's twin, but it's a hell on Earth, or hell on Venus. Right. So from a philosophical point of view, does it bother you to look at the moon and it's so different from Earth?
No, I love the moon. I love looking at it and thinking about how it forms. Just the fact that it's still not totally resolved, even though humans have walked around there already decades ago. I think it's amazing in a good way. And the other thing that I think is what I really like about the moon is every human being can see the moon, but not everyone realizes that its formation is directly linked to our own planet's history. I mean, the planet Earth was hugely affected by this massive impact, if it occurred in the way we think it occurred. That really reset sort of the history of our own planet. So it's not just that the moon was formed, but also the Earth was affected enormously by this impact.
Could you argue that we would not be here today without that moon impact, or have people tried to argue that?
Yeah, some people try to argue that. That's very difficult to say. It is true that the moon has some effects on the Earth which are beneficial, like for example, tides are nice to have for life. The moon is relatively big and close to Earth, so it stabilizes our rotation axis. That helps to bring more stable conditions on the surface, which we think are good for life. But that doesn't mean that I think that life wouldn't be here without the moon. I think that's a bridge too far.
Well, thank you so much, Wim, for your time this afternoon. Appreciate your generosity. Thanks for letting me have a look around the lab. It's impressive, and continued good work.
Well, thanks a lot. Nice having you here, and hope to see you again.
Thank you.